Hello and welcome back to Unbounded Operators, the video series where we talk about interesting operators coming from functional analysis. And in today's part 8, we will talk about the general concept of adjoint operators. These adjoints exist in two forms. On the one hand, we have the Banach space adjoints, and on the other hand, the Hilbert space adjoints. In fact, these two concepts are not so different, and we will define them in this video today. However, before we do that, you already know, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter, you can download additional material with the link in the description. Okay, then let's start, and first we should recall what we already know for bounded operators. Indeed, from the functional analysis series, we already have a nice definition in the case that we work in Hilbert spaces. This means for a bounded operator T, we can define an operator T star. And this T star changes the direction, so now it goes from y to x. Of course, often we have that y is equal to x, but this adjoint T star also makes sense for different Hilbert spaces. Simply because it's defined by using the inner products. So we have that y in the inner product with Tx is equal to the inner product when we push this t to the left. And there we actually have t star, and the equation should hold for every y and x. And we can also be very precise. Here on the left hand side we have the inner product of y, and on the right hand side we have the inner product of the Hilbert space x. So this is how we define the Hilbert space adjoint, and you see it only works for bounded operators in this sense because we don't consider any domains. But if we want to do it for unbounded operators, the idea should be the same, which means changing the position in the inner product. But before we do that, let's also talk about the more general Banach space case. Actually, the next definition is more general than the one before, but it's also a little bit different. And we also see that in the notation because we call this adjoint operator T prime. Moreover, it also changes the direction as before, but now it's defined on the dual space. So it maps y prime into x prime. Hence, this means the input is a continuous linear functional defined on y, and the output is a continuous linear functional defined on x. So you see, it's a different concept than before for the adjoint, but you also know the Riesz representation theorem in Hilbert spaces. It tells us that we have isomorphisms here, and therefore T star and T prime for Hilbert spaces are related. But now in the case that you only have a Banach space, you cannot use the inner products for your definition. And that's the reason we have to work with our linear functionals. Now by definition, what we get out here is a continuous linear functional defined on x. This means if we put in a point x, we get out a complex or real number. Therefore, you should recognize that this combination here is very similar to our Hilbert space case here on the right. Therefore, our T prime should be defined by pushing the operator T into the equation. In other words, this should be y prime of Tx. And there you should see, we don't have a problem. We can use this equation as the definition for T prime. We just have to say that it holds for every functional on y and for every point x in x. So there we have it. This is our adjoint operator, and it sends linear functionals to linear functionals. And this concept is quite important because you already know that for the LP spaces we have nice isomorphisms for the dual spaces. This means that it could happen that for analyzing an operator T, it might be helpful to go to the adjoint to get the information. And moreover, we already know for Hilbert spaces that self-adjoint operators are very important. Therefore, the next question should be, can we extend these definitions to the unbounded case? Which means that in both cases we have to bring in the domains. And indeed, these domains already make more problems. However, I would say we can immediately start with the general Banach space case. And there the assumptions are the same as always. We have two Banach spaces and a linear operator with domain dt. However, here we should assume that the operator is densely defined, which simply means that the domain in the Banach space X is already very big. Or you could say the Banach space X is not bigger than needed for the operator T. And now in order to give a definition, we can just write that the domain dt is a dense subset in X, which simply means if you take the closure in X, we get out the whole space X. Hence, it also includes the case that the operator is defined everywhere. And now in fact, this property guarantees that we have a well-defined adjoint operator. And this operator we also denote by T prime. However, now it's also an operator with a domain. And now it makes sense that this domain lies in a dual space of Y. And moreover, the dual space of X should be our codomain. And now since we want to call it the adjoint operator, it should fulfill the same equation as before. Which means if we have a linear functional y prime and you put in tx, it should be the same as t prime of y prime of x. And since this combination t prime y prime should give us a linear functional on x, we want to have this equation for every point x in the domain of t. And please don't forget, dt is a dense subset in X. But obviously, the y primes here are restricted to the ones from the domain. So only with this restriction, the equation makes sense. Hence, this proposition tells us that such a nice adjoint operator exists. And it turns out that we also have a uniqueness result because the domain can be chosen in a maximal way. In other words, this proposition tells us that there is a uniquely defined adjoint operator with a maximal domain. And this is exactly what we wanted to extend the definition of the adjoint. And now the proof is actually not so hard because we only have to define the domain in this proposition. Which means we have to take the suitable functionals for this equation here. And then the question is, how can we do that? So which functionals y prime are good enough for us? Now, since we want to get out a functional on x, it makes sense to claim that here. So we could just say, if we find such a nice x prime, we are good. To understand what this means, please don't forget that we want to have this equation for every point x. Which implies that this combination we have on the left should be equal to a linear functional. Hence, it should be equal to our x prime here. And as I already told you, we want to have it for every x in X. But we immediately see this is not possible because t is not defined on the whole space X in general. Therefore, the natural restriction we have to do here is to say that we have this equation at least on the domain of t. It's just not possible to check this equation for points x that don't come from the domain of t. So this is the condition for y prime. We want to find an x prime such that y prime with t combined is equal to this x prime. And then we can actually do the mapping and say, yeah, this x prime is the image we want. Hence our t prime of y prime should be equal to this x prime. And that's already the whole thing because we have a domain and a linear operator. And moreover, we also see that this domain here definitely contains the zero vector. The zero functional is included here, so the domain is not empty at all. However, this is all we know at the moment because it could be a very small domain. Now, this is not a problem for us here, but we can see a problem in the definition here. In particular, we don't know if this is well defined. Indeed, it could happen that we find two different functionals x prime here that still fulfill this equation on the domain of t. Therefore, I would say let's check that. Let's assume that we have two functionals x1 prime and x2 prime. And both of them should satisfy our equation we want to have for all x in the domain of t. And since the left-hand side here is the same, we can conclude that x1 prime is equal to x2 prime. However, we still have the equation only on the domain of t. But this is not a big restriction for us because we still have linear functionals here. And we use that and put them together to the left-hand side. And then we see that we have a linear functional here on x, which is 0 for a dense subset. And since we know it's also a continuous function, we can conclude it's 0 everywhere. To say it more precisely, we can approximate every point in x with the dense subset, and the continuity does not allow us to have different values there. So the conclusion is clear and good here. x1 prime and x2 prime were the same from the beginning. So you see, we have a well-defined operator t prime. And moreover, we also see that we cannot make this domain any bigger because all functionals are already included. So we have also shown that this domain is the maximal one. Okay, so very good. The Banach space adjoint is defined now. And now I would say, let's also write down the definition for the Hilbert space adjoint. From the beginning, from the motivation from the bounded case, we already know this should be very similar. Hence we can take exactly the same assumption, but now instead of Banach spaces, we take Hilbert spaces. Most importantly, we also have a densely defined operator here. And now we want to have an operator t star, so let's start with the domain first. T star should map from y to x, so let's take all the vectors from y which are good for us. So the whole thing should be exactly the same as before, just without mentioning dual spaces. Therefore we don't take a functional here, we take a point x tilde from our vector space x. And then what we want to do in this inner product for every point x in x is that we can push this t to the left hand side. In other words, we want to get out x tilde together with x in the inner product. And as before, this should work for every point x that is possible, which means for every point x in the domain of t. And then it's possible for us to define the operator t star, just by saying that t star of y is equal to this x tilde. And indeed, with the same proof as before, we can show that this whole thing is well defined. But please don't forget, to get this, we need a densely defined operator. Exactly for these operators, we could show that both adjoints exist. So we have the adjoints with the largest possible domain. However, we already asked that before, how big is this domain actually? It's not clear at all. It could be just the 0 vector in the worst case. This is definitely something we don't want to have, because then the adjoint operator does not help at all. If the domain is just the 0 vector, then there is no information hidden in t star. So analyzing t star does not get us anything for t. Therefore, it's important to know which assumptions we need to ensure that this domain is big enough for us. And that's definitely something we should discuss in the next video. So I really hope we meet there again, and have a nice day. Bye bye.